Good morning, good afternoon, good evening, ladies and gentlemen. Welcome to another series of online lessons. If you haven't already, please subscribe to the channel and leave a like for this video. Now, in today's lesson, we are going to review this tutorial sheet from Multivariable College of Education. And the activity basically is on multivariable calculus, and we are using the chain rule, the multivariable chain rule. Okay. So we've done most of these questions, and now we're going to do question number 4 and 5. Yeah. So for this one, we are asked to calculate the volume of, or we've been given that the volume of a rectangular solid of dimensions L, W, H is given by this. So this is the volume of a rectangular solid. Find the rate at which the volume is changing when L is 50 and is increasing at a rate of 0.2. The width is 40 and is increasing at that rate. The height is 30 centimeters and is decreasing at that rate. Okay, so now as per previous lesson, we know that to find the rate of volume, which is the rate of volume, we just find dv dt. Okay, so when you look at the formula, v has three variables, that is L, W, and H. And L is changing with respect to time, so it only has one variable. W is only changing with respect to time, and H is changing with respect to time. So at the bottom here, we see that we only have one type of variable, so this will be a full derivative. And how we're going to form the chain rule will say, how do we get from V to T? How to get from V to T, we say V with respect to H, then H with respect to T. So that is V. So V with respect to L, V with respect to L, there are three variables here, three different variables. So this will be a partial derivative. So that will be partial of V with respect to L. And L with respect to T, there's only one type of variable here. So that is a full derivative, that is L with respect to T. Plus V with respect to W, that will be a partial derivative because we have three variables here. So that will be V with respect to W, then W with respect to T, that will be a full variable. So that will be dW dt. Then here we'll say plus. So we'll say plus. How do we get to? So we say V with respect to H. So that will be a partial derivative. So that is V with respect to H times H with respect to T. Okay, so that will be our chain rule here. So now from here we just replace in the value, the variables. So we have our V is equal to LWH, so that is LWH. So I would say V with respect to L. When we say find V with respect to L, the L will remain with WH. V with respect to what? To W. So V with respect to W, that will just be LH. And V with respect to H, that will be LW. So now we just plug in these values here. So we have V with respect to L. So V with respect to L, that is WH times L with respect to time. We have L with respect to time. So the length L, what is L with respect to time? So find the rate at which the volume is All right, so L is 50 and is increasing. So L is increasing. So increasing, we say positive. So L is increasing at a rate of that. So L is increasing at 0.2. So we say that is positive 0.2. Decreasing is negative. So we say plus. The V, the W, so V with respect to W, that is LH. That is LH times W with respect to T. So W with respect to T, the width is 40 and is increasing as well at that. So is increasing, that is positive 0.1. If it was decreasing, that would be negative. Then we say plus the V, the H, V with respect to H, that is L, W times H with respect to time. So H with respect to time, that is, where is H? And H is 30 and is decreasing. So decreasing is negative. So that would be negative 0.1. Okay, so H is decreasing. So that would be negative. And now we just plug in the variables of W and H and L. So L is 50. So this will be equal to W. Where is W? W is 40. So that will be 40 times 50 times 0.2 plus L. L is 50. So that is 50 times H. H is 30 times 0.1. So this, because of this negative, this would be negative L times W. L is 50 times W, which is 40. Then times, since the negative comes here, we have times positive 0.1. All right, so from here we simplify. We say 40 times 50 times 0.2. So we work them categorically like that. So we simplify this. All right, so this here will give us 400. This here will give us 150. And this here will give us 200. So we simplify everything. This will give us 350. Let me just confirm. So this is, yeah, it will give us 350. So 350, what units are we using? So that is liters. Or is it this one? No, it's not this one. So we're using centimeters. So that will be centimeters cubed per second. Okay, so that will be the value of the change in volume with respect to time. Yeah, so that is the rate of the volume. So we can also just have an intuition of how to solve question 5, or let me just do question 5 as well. All right, so we are on question 5. Question 5 says the pressure, this volume in liters and temperature in Kelvin. So P is for pressure, V is for volume, and T is for temperature. Of a mole of an ideal gas is related by this equation. Find the rate at which volume is changing. Okay, the rate at which volume is changing. So you see this formula, we need to make V subject of the formula. So making V subject of a formula here, to make V subject here, we just say V, excuse me. So we say V is equal to 8.31 T times 1 over P, or P to the negative 1. So we simply multiply throughout by the inverse of P. So inverse of P times that will be P to the power 0, which is 1. Then we remain with the P to the negative 1 here. So, or we say V is equals to PV is equals to 8.31T. We just say over P, of which we can write this P as P to the negative 1. So now what we're looking for is the rate of volume. So the rate of volume, that is the rate of volume, which is the V dt. Okay, the V dt. So when we look at our volume here, V has two variables, that is temperature and pressure. Okay, and pressure is increasing at the rate of, so T is that, and it is increasing at the rate of that, and pressure is that, and it is increasing at the rate of that. So pressure has time, and temperature has time, and pressure has time as well. So now V with respect to T, how do we move from V to T? We say V with respect to temperature. So there are two variables here, so it will be a partial variable. So there are two variables here, so that will be partial V with respect to T, which is temperature, times temperature with respect to time. Okay, then we say plus V with respect to P with respect to time. So that will be a partial. So V with respect to P will be a partial because there are two variables here again. Then we say times dP. These will be a full variable. Let me just write here, times V, the temperature dt. The temperature dt will be a full variable because temperature to time, there is only one variable here. So we say plus as well. So V with respect to P, that will be a partial derivative because there are two variables here, times dP dt, because there is one variable, so it will be a full derivative like that. So now we just need to find V with respect to T. So this is our V. So V with respect to temperature. So the temperature will be gone here. We'll just remain with 8.31, then P to the negative 1. Okay, then times the temperature the time. So the temperature the time, so the rate of temperature. So when temperature is that and the rate is increasing at that, so increasing, that is positive. So we say positive 0.05 plus V with respect to V, what is the volume with respect to P. So we differentiate V with respect to P. So V with respect to P, we are differentiating this. So it will be 8.31T. Then differentiating P, that will be dropping the negative. So it will be negative P to the negative 2. So that will be the derivative. So that will be negative 8.31T times P to the negative 2. Okay, so it will be like that. Then times the P dt, pressure with respect to time. So pressure is also increasing at that rate. So that is increasing at 0.02. So now we just simplify everything. Let me just write it here. So finally, our dV dt will be equal to, so this is 0.05 times that. So that would be 0.05 times 0. That is what, 0. Is it 8.05 0.05 times 8.31. So that will give us 0.4155. Then we have a p to the negative 1 here. That, or it will be minus because of the, so here we also simplify. So we're going to have minus here. Let me see. So minus 8.31 times 0.2. That is 8.31 times 0.02. So that will give us 0.1662. There is temperature here and there is pressure here to the negative 2. Now we have been given the values of temperature. So temperature is that. So temperature, let me just put it here. Temperature is the pressure is and the pressure is 17 kilopascals. So that would be 17K. 17K. So that would be, okay, so we'll just say 17 kilopascals. So it is measured in 17 kilopascals. So we'll just leave it as 17. Then we just replace now. So this is 0.4155, 17 to the negative 1 minus 0.1662 times the temperature, which is 315, times 17 to the negative 2. Okay, so we simplify everything here. So that what is 17 to the negative 1? We can just punch that directly on the calculator. So we have that. So we find 17 to the power negative 1 times that. It will give us that. Then 17 to the power negative 2 times that, it will give us that. Then we simplify everything. So notice that I have not rounded off. So rounding off should be done at the end of the question. So here we're going to have, so we see that we have a negative 0.156. So that is a decreasing. So that is approximately negative 0.1567 liters. I'll just say L per, I'll do right, liters per second. So that is the rate of the volume. So the volume is decreasing. So the volume is decreasing. So the volume is decreasing. So that is about it for these questions. We move on from here and we are done with this tutorial sheet.